Okay, hello. I'm going to go over the two PowerPoints. One of them we've already done in class for first order differential equations and for second order differential equations. I've already annotated up the PowerPoints, but as I talk through the slides, I'll make some additional annotation. The first one that we want to look at is basically sort out the terminology, and we're going to look at first order differential equations, the principle of the natural response to the differential equation and the forced response, okay, and how that natural response leads to the complementary function and the forced response leads to a particular integral. So that's the first set of PowerPoints. So in order to explain what a differential equation is and how it is different from equations you have met in previous work and why it is important for an engineer to know how to solve differential equations, we start with a simple example. And the example that we have is this cool-in problem here. So we've got a change in temperature. So that's here. So the temperature changing with respect to time. The body is in an environment where it's at 20 centigrade, and I think what we got is we got a body that's initially hotter. So we've got, for example, initially at 60 degrees, so 20 minus 60, and you can see that's going to give you a value of minus 40. Alright, so minus 40 times by a constant, which we assume to be a positive constant. K is positive, so this is telling me that the rate of change of the temperature, which is initially at 60, is in some way dropping because it's a negative gradient. So that's our model, and we can see that if our temperature goes, for example, below 20 degrees, so it's dropping down to 20 degrees, and if it goes below that, then this difference here will become, let's say it drops and it actually gets colder than the environment, then that value there will become +1, and that means that we expect it to have a rate of change to make it go hotter. So in some way that this gradient is this equation is telling us that the system's going to drive most likely such that there's no real reason why it should drop below 20, such that it's going to drop from the 60 centigrade and it drop down and then it hit the 20 centigrade. So that's the problem that we're setting up here. So I'm going to write out this equation. So this equation is called made up of it's a differential equation because it's got a derivative term in it, and what we want to do is find a value, a function for t with respect to time. So this going from an equation which got a derivative to it to an equation where there's no derivative means in effect we're doing integration. Okay, so we're using an integration technique to get from an equation with the derivative to an equation with just variables. So it turns out that the solution for the above equation can be given as this term here, and I think that later on we're going to derive it or prove it. Whoops, jumped over a slide. Right, so here we're going to prove it. So what we're doing here is we're not working out from this equation how to get to here, but we're saying, let's say that you do know that this is the equation that you want to use. Can you put this equation into the differential equation and show that it works? So if I take this equation and differentiate it with respect to time, so I'll take that equation and differentiate it. So I'll differentiate the 20 and I'm going to get 0. Differentiate the 40 exponential minus kt, and then that's just going to make my plus become a negative, so I end up with minus 40k exponential minus kt. So simplified, that equation differentiated here is going to lead to this expression. So that tells me what this should be here. So I can then then start comparing my equations. What I'm going to do is now look at the right hand side and take this equation and then put this into the right hand side. So the right hand side, we've got the k, we're going to open our brackets, put 20 minus t in there, and then we're substituting the t into this bit here. So substitute that in, so that's going to give me 20 minus, open the bracket, 20 plus 40 exponential minus kt. It will go in there, so that's my t bit. Now we want to simplify that, so we're going to have the minus k 40 exponential minus kt, and so what I've done now is I've created a left hand side and I've created a right hand side, and now I can compare the two. So that's my left hand side here, and now I can compare that to my right hand side, and I see that they're both the same, so I'm happy. Okay. For this equation, we've got y is exponential minus 2t. Can you prove that that function will satisfy this differential equation? Notice we're not going from here and solving this. We're saying, does this function here, if we put it into this equation, does it work? Right, so we first of all we'll substitute the y expression into the two components that I've got on the left hand side. So I've got delta t d delta t, then the y equation, plus 2y equation. Okay, so for the this term here I need to differentiate it, so the minus 2 will come out of the front, so that's it differentiated, and this equation here in brackets I just need to multiply by 2. So we can see we've got two terms that look exactly the same, equal and opposite, so we're going to get 0. So the left hand side is 0, the right hand side is 0. So it would seem, yes, if you take this equation and you put it into this equation here, then that will satisfy that equation as a possible solution. Do you notice that there's that's not saying that's the only solution? For example, a very easy way to solve this equation would be, say, let y equal 0. If I differentiate y equals 0, that will also give me the value 0. So that gives me 0 plus 2 times 0, when I put it into this equation here, equals 0. So I've got 0 equals 0. So there you go, I've got another solution that could work. Right, so I guess what I'm saying here is that this technique to solve differential equations doesn't necessarily mean that we've found all the terms, doesn't necessarily mean we find the right equation, but we've found a possible solution. So more generally speaking, we can get rid of the 2 and replace it with a c, and then substitute it into a more general form of this equation here. So this is called a first order differential equation, because we've only got the derivative to the first order. We've got y there, and stuff in front of y is just got a constant. There's no x terms or t terms, no other variables. And that's important for what we've got on the left hand side. The left hand side can only be a function, essentially speaking, of the of y, with the exception of the derivatives. So the derivatives are allowed to appear on the left hand side, but no other terms. So I couldn't consider, for example, delta y over delta t plus 2kty. Okay, so an equation like that is not a general result. Anyway, so let's come back to this. So we're going to substitute this equation into here. So we'll put it into there, at that point there, and then we're going to put it into this point here. This bit here, straightforward. All I want to do is the k times by the expression, so that leads to that term there. This correct expression here, I just want to do the derivative. So take the derivative means the constant minus kt that goes out at the front, and then you can see again we've got like terms here and here, got them, but they're equal and opposite. So the left hand side equals 0, the right hand side we know equals 0, so that expression will satisfy that differential equation. So again, we're happy that we could propose that that is a possible solution to that differential equation. Now let's consider first order differential equation where on the right hand side we've got some kind of function of the variable that we're differentiating with respect to. So this equation we're differentiating with respect to x, and we're going to put some function on the right hand side. This time I'm going to use a trig function cos x. So to solve this differential equation we need to find the function y, which when differentiated with respect to x produces the result cos x. So what I'm doing is I'm solving this equation by second guessing what the solution is. So I could say, well, if I put y is sine x in there, if I differentiate that, what do I get? Well, I should know about differentiation, and I can look up my differentiation tables, and if I differentiate sine x, I'm going to get cos x. Okay, so that's fine. What about if I put y equals sine plus 1? Differentiate that and put that in. Does that work? And then I notice again that works. Okay, differentiate the 1, I'm going to get 0. Differentiate the sine x, I'm going to get cos x. So that's also a solution. And of course we can do this to infinitum. So in general we can say that y sine x plus c is going to be a solution to this equation. Yeah, so we've solved an integration here by using our differentiation techniques. So this is kind of an important result, because we're showing that differentiation here is anti-integration, as it were. The order of a differentiation equation is the highest derivative. So when I refer to the order of my differential equation, I look for the highest derivative term. So that's basically going to be for the d, and then we notice that we're going to get for the d on top we're going to get a little number. Here it's 2. So that means that this is a second order differential equation. And it's it's always going to be the number next to the d on top that I'm looking for when I name my differentiation equation, for saying what order it is going to be. So here it looks quite complicated, that we've got this delta s over delta t term here which we're squaring, but in terms of naming it we ignore all that, and we're only interested in this bit here, d, and we see that we've got that, raising that to the power 2 as it were, and so that's a second order differential equation. This one's not straightforward to solve. This one here, we've got looking at how a pendulum acts. We're assuming there's no resistive forces, and the angle is dependent upon the second order differential with respect to time, plus the natural frequency of the pendulum squared, and then the angle there. So this equation here is the second order differential equation. We've got the 2 there. Here we've got in effect d to the power 1 there. So here we ignore this term, and it's, in terms of naming it, we say again that is a second order differential equation. So determine the following differential equations. So here you can see there's going to be a second order. Here it's going to be a third order, and here, although we've got v squared, what's important is the thing next to the d, so again that's going to be a first order one. For d by itself, remember d by itself you're going to have to put the 1 in for yourself, so that's the first order. Differential equation is linear if the dependent variable and its derivatives occur to a single power only, and there are no products involving the dependent variable and or its derivative. Also, no non-linear functions of the dependent function such as sine, exponential, etc. occur. Right, so what does that all mean? Best thing is to look at examples here. So here we have good examples of linear equations. So first of all we're naming the order. Next we're naming whether it's going to be a linear or a non-linear equation. What I need to do is basically get my highest order derivative such that it's got 1 in front of it. Yeah, so there's no other terms here. Then I can examine the equations I've got. What I want to do next is try and bring all the terms which I'm trying to integrate. So here we're trying to integrate y, so we want to bring them all onto the left hand side, and any other variables that aren't to do with the variable that we're integrating onto the right hand side. So here we don't have any except for the derivative term, that's allowed to be on the left hand side. So here we don't have any, so that's a straightforward, in fact this is called a homogeneous linear for second order differential equation. Here we've brought all our x's onto the left hand side except for the derivative term. There's t squared appearing, and that's going to be left onto the right hand side. That we're not bothered about whether it's a linear or non-linear. We're only interested in this bit here, and what we're doing is we need to then look at all the terms in front of the x. This term in front of the x is just a number 2, so provided the terms in front of the your expressions here, whatever they might be, provided they are going to be just numbers, then it is a linear equation. And here we have a nonlinear equation. I've brought all my v's over to the left hand side. So the first problem I've got is that the v in front of my derivative is not a 1. Second problem that I've got is that this one here is v squared. So you could kind of consider that this is kv in a bracket times v. So we're looking at what's in front of the v on the left hand side, and we see that we've got kv here. We're looking at what's in front of this expression here, and we see that we've got v here. So that means that there's some kind of function. In this case it's a function of itself that's in front of it, which makes it into a nonlinear. If this was, I know, some kind of function of x, again, that would make it into a nonlinear equation. So what's linear and nonlinear? So here we've got nonlinear. So what we need to do is imagine splitting up the v. So, and we say what's in front of our v there, it's another v, so it's nonlinear. Here we've got 3 in front of that derivative, a 5 in front of that derivative. This guy can be kicked over to the right hand side, no problem, it's linear. Okay, in front of my highest order differential term that I'm looking at, I've got something which is a function of itself, so delta x delta t, so then that's going to be nonlinear. And also I've got a problem here as well. I could rewrite this as tx. So look at what's in front of the x term, and we've got a t. T is a variable, so that also makes it a linear, non-linear. So there's 2 reasons why this is nonlinear. We only need 1. Here I can take this term, take it over to the left hand side. This frequency term here is a constant frequency, so therefore it's a constant number, so that makes that a linear equation. To solve a differential equation, we need to reverse the process of differentiation, as we've seen previously. The solution of a differential equation is performed using integration techniques. So this is some sort of expression that we might want to integrate. I can split up my differential term straightforward, bring it over to the right hand side, and then put integrals on. Because I'm simply integrating delta y, that will drop down and become a y term straight away. Now integrating the other term on the right hand side, I need to put an integral in because I need to think about it a little bit more. So I put an integral sign in front of it, and then put my dx term there. Note that if we had an additional term, we can say we had that, for example, y at some location equals b. We could put that on, so they've kind of done it there. So if what am I trying to do here? I'm saying that I've got a start location here a, which I'm integrating with, and I'm integrating to the limit x. So I'm going to integrate this term here on the right hand side, and I'm going to stick on a constant. Okay, now the reason why we're making this point that we can stick on a term to integration there and they're all going to be valid solutions is that if we were looking at the solution here that we're trying to solve this one, so we're going to integrate that, the integral is going to be half x squared plus a constant. this constant is arbitrary. So this solution here is we've got an infinite number of solutions that can be put into this differential equation and it will still work. So where that constant is located could be at various points. So it's described as a family of solutions are possible. When you have decided, no, I definitely want y to equal 0 when x equals 0, so it's at that point there, my constant therefore will be 0. In that particular case we call that a particular solution. Okay, so a particular solution is different to a general solution. This is an example of a general solution where we have a constant there and we haven't decided a particular case that we're going to use. So that's a general solution. When I've decided that I want y to equal 0 when x equals 0, then that becomes a particular solution. So let's look at this term here. I'm going to integrate it, so that should be straightforward, and then we apply, I'm going to refer to them as boundary conditions. We're going to apply boundary conditions to decide what the C is going to be. The boundary condition in this particular case, I use the notation BC. The boundary condition for this case is that y equals 2 when x equals 0. So what you need to do to work out what C is, you substitute those values into your equation, and then that will tell you what C is. Once you've got the C, you can rewrite this equation here, the general solution, and then you have got the particular solution here. Okay. So here's an example I'm going to do. So I'm going to integrate the left hand side, so I'll sort of do that formally, and I'm going to say that well, in this particular expression I've said that I've in effect put delta x on both sides and then put the integral sign on both sides. And so that means that on the left hand side that becomes the integral of delta y, that just becomes y, and then on the right hand side we've got more interesting stuff going on there. So we need to integrate the x, the sine, the 1, and because we've got no limits here, we're going to put the c on, and so that will give us a general solution. And the boundary condition here is given here, so that means when x equals 0, y must equal 5. So y equals 0, and then we put in what x when x equals 0. So I've got a 0 there. I put a 0 into a cos, we end up with a -1. Put a 0 into an x, going to end up with a +0. So we end up with just +0 there. So that means we've got the 5 -1. Take that over to the left hand side, so c equals 6. And so there we've got our particular solution. So we're going to look at some equations in this form here. That's a constant, that's a constant, and this is going to be a first order linear differential equation, and that's pretty much the only kind of equation for this course that we need to worry about solving. The problem we're going to look at is an engineering one here, where we're looking at the current, and it goes through a resistor, an inductor, we've got a power source, so that means we've got an AC alternating power source. The voltage going across the resistor is the current as it were, times by the resistance, and the voltage going through the inductor, well, we need to know a little bit about engineering, but it's the differential of the current times by an L term, and L is called the inductance. Okay, so basically the voltage, I know what the voltage is over those two bits of components in my circuit. So the voltage that I'm applying needs to equal the voltage over the inductor plus the voltage over the resistor, and when I switch it off, when time equals a certain time, I've decided I'm going to switch it off, and then I'm going to have no voltage applied. So if I'm going to go from that scenario to switching it off, so actually I was said that there was an AC current. We're actually looking at the problem of DC current and switching the DC current off, so made a mistake there. So we will switch it off, and then we're only going to have the voltage over those two components. We're going to have no power supply. Let's rewrite this so that we have a 1 in front there. So we're going to bring the L term, divide it through, and then we've got these variables in front of my I. So we're trying to make our equation look like a first order differential equation where we've got 1 in front of the leading derivative term, and we can go back to our general result a few slides ago, where we know that if we put this expression into this equation, it will work, where the C is going to equal to it's K, where the K is going to equal to minus R over L, the term in front of the variable that you're integrating. Okay, so this is the solution to this equation here. We've proved that, or not proved it, but we've shown that equation satisfies the differential equation above. So more generally, we can replace the y with i's, the t's, they stay the same. The only thing we need to replace is that constant there, and so we're going to replace that with minus R over L. So the current should behave like this. Well, we don't know what that C term is. The C term we'll replace with the current is going to be the initial current when time equals t0. So we can replace it with that. I'm going to simplify that expression, and I'm going to put in t minus delta 0. Now if you want, you could consider delta 0 to be 0. It's arguing that's when I've switched off, but in actual fact we're saying that we've done the experiment, and at the third second we've switched off. So in this particular case we've switched off at 3 seconds. So what's important is that this t minus t0 is just getting the datum right for the time location. Okay, it's got nothing to do with constants or anything like that. Where the constant that we've used is just this t0, and that's simply going to be whatever the current was at that particular point in time, and that apparently it's 1 amp. So we would expect the current then to behave in the system that it decays away like this over a period of time. So on that previous problem, we had a homogeneous equation, meaning that this expression here was set to 0. Okay, so what we've seen from that term is that our function that we're applying over a period of time is not necessarily 0. So for example, we could be not looking at a simple DC current, but more typically, if you've got something with inductors in, you'd imagine that you'd be looking at an AC current. So that thing that we could be having on the right hand side is they're referring to it as a forced response. Okay, so they're saying that you can set this thing here on your left, set it to 0, and you're going to get what's called the natural response of the system. How the system will respond naturally if there's no external forces, or in this case external voltages, being applied. And you can consider these two things to be independent, and you can just add up the two results together. So you can add up your natural response and your forced response, and that will be your total solution. That seems a bit of an odd thing to say, that you can simply just add these two things together, that they don't interact. Well, imagine that I wanted to integrate, I will do this with respect to x. I wanted to integrate this term here. Okay, so integrate that. Well, that's not a problem. Yeah, I know that that's going to give me a solution of a half x squared plus a constant. Okay, well, now let's say no, I actually want to integrate x plus x squared. Right, okay. What I can do is I can integrate this result, and then I can integrate this result. So I could say, well, let's consider this to be that problem, and that problem. Right, so let's integrate this, and the solution, I'll call that y1, y2. So y2 equals a third x cubed plus a constant. y1 I've already shown is half x squared plus a constant. So if I want to integrate this term here, which I'm going to now call y, well, the result is half x squared plus a third x cubed plus c. So you can see with integration, you can simply add your results together. So you find the result. In this case, we're going to find the result for the left hand side, integrate it, and that's going to be our natural response. And we're going to integrate the right hand side, and that's going to be our forced response. Add those two results together, and we've got our solution. So we're going to break this down into two parts so we don't confuse ourselves too much. We're going to integrate the left hand side, and we're going to call the solution to that the complementary function, and then we're going to integrate the stuff on the right hand side, and that's going to be called the particular integral. Right, so in order to determine the natural response to the linear system, so when we're presented with this differential equation, the first thing I need to do is ignore the thing on the right hand side. So then it becomes this equation here, homogeneous first order, in this case first order linear equation. I'm going to solve that, and then I'm going to then examine this, integrate this in effect on the right hand side, and add the two solutions together. Okay, so the expression that we're looking at is that if this was z 0, or if we set it to 0, then the equation becomes what's called a homogeneous equation. If this expression on your right hand side is not set to 0, then it's called an inhomogeneous equation. So here we've got a straightforward homogeneous equation. We've seen this result before, and we know the solution is going to be that. Okay, this one here, we've got the 2 in front, so what we want to do is rewrite this so that our leading term becomes a 1. So divide through by 2, so that then becomes a half. We know the result. We've got standard result to solve an expression that looks like this, which is the yc what's it going to be, minus kt here, where k is going to be a half. Okay, so we're happy solving these equations on the left hand side. We can do them all day. All we need to do is make sure that the a term here is divided through when we set this to be 0. So that's all the left hand side sorted out. What about what's going on the right hand side? Well, again, I want to use, if you like, anti-differentiation here to solve what's going to be the integral for the right hand side. What I'm going to do for that is I'm going to guess a solution that I can put in into the equation on the left hand side that will give me the result of the right hand side. And in a way, that was the very first thing that we were doing when we were looking at simple problems, which were essentially speaking variable separable problems at the very beginning. So what are the functions that we need to guess to put into the right hand side that will work, and when we put them in the differential equation on the left hand side will give us the right hand side result. You get tables here, cheat sheets that you can use. If the expression on the right hand side is a simple constant, then the value that you want to guess is, we're using the expression constant here, so p. If there's some kind of a polynomial, what you want to do is look for the highest term of your polynomial, and then you have an expression which has that highest term and then all intermediate terms. So if, for example, on the right hand side it was t squared, your guess for your expression that we're going to put into the function will be pt squared q. So even though there's not a q on the right hand side, we're going to guess that we might need it as a possible term to put into the left hand side, and then the next term down there, an r. Okay, if we've got something which involves, let's say, sine omega on the right hand side, then we want to put in two trig terms. We want to put in the sine, and we also want to put in the cos. So the reason why we're putting the sine and the cos is because we're differentiating the sine, and we know that when we differentiate a sine, we're going to get a cos. So I need to look at the both possible terms there when I put it into the left hand side. So I'm going to do a straightforward one here. The left hand side should be straightforward. I know how to do that. I've got my standard result. So that's the y equals c minus 2, we're doing with respect to t. So that's going to be my left hand side solved, and that's going to be called the complementary function. Okay. For what's going to go on the right hand side, I'm going to guess that if I put in, and I'm going to call it particular integral. If I put in set the particular integral to be p, and then put this expression into the left hand side, I will end up with this result for the right hand side. So we could say that y should really use subscript pi or p to represent that that's a particular integral. We're going to guess that's the result. Next thing we want to do is differentiate that result, and we get the 0. Then we get the two parts of the cake that we need to make up this equation. The first part of the cake is saying that it's 0 plus 2, and the second part is saying that y equals p. So that gives me 2p on the left hand side, and that needs to equal 4. So therefore p equals 2. So the actual particular integral is that y equals 2. So here we're going to bring both parts together. We've got the complementary function, that's the natural response part, plus the particular integral part, and our general solution is therefore going to be the complementary function. Notice that we've got this constant here, and we've got we're sticking on the particular integral bit there. Now to go from, watch out for the words particular, okay, so now I'm going to use the expression particular solution. Particular solution does not mean particular integral, okay. Particular solution is that in that previous slide, the C has now been worked out. So that's, we've got a family of solutions. We could set C to be an infinite number of values. In fact, we could even possibly set C to be 0. That's a possible solution. So the next thing is that I need to have a bit more information, and where, for example, what y equals when the time is 0, and then I can find the particular solution. I can find that constant. So this is going to be my expression. I'm now going to say I know that y equals 1 when the time equals 0. So in that particular case, I'm going to set y equals 1. I'm going to set the time to be 0. Exponential raised to the power 0 going to give me a 1. So that gives me 1 plus the c plus the 2. Rearrange the 2 to move it to the left hand side, so the constant is going to be -1. So now let's put the -1 back into this result, rearrange it so it looks a bit nicer, and then we're going to get the particular solution to that problem. So here's some more involved examples here. So for the A problem here, first thing is I find the complementary function. That should be straightforward. The particular integral, well, I need to look at the term on the right hand side, and I assume that y could be at plus b. I need to differentiate my result there, put both of these expressions back into my equation here. So put the differential bit in there, the y bit there, and we go back and we set it to t. We're going to end up with constants here, so we need to collect. What have I done? We need to collect, for example, t to the power 0 terms, i.e. constants which don't have t next to them, so that's going to be the a and the b. So a plus b needs to equal 0, and then we can collect the the terms with t next to them. So in that particular case, we're going to have that we're going to have an a there equals 1. Okay, so that's collecting terms where we've got t to the power 1 next to them, so that's that term there. and what's next to the t? Well, it's a 1, kind of hidden. So a equals 1. The previous equation that is a equals minus b, so b equals minus 1. So that's that solved. Here we're at the stage where we've got what's called the general solution. Now we're going to apply the boundary condition. So when t equals 0, y equals 1. So y equals 1 when t equals 0. So I put 0 into this expression here. That then leaves me with that's going to equal 0. So we're going to have 0 take away 1 equals c. Bring our minus 1 over to the left hand side, and that will give us c equals 2. So c equals 2, let's put it into our general solution, and then we've got the particular solution here. This expression here, the complementary function, straightforward, you can write it out straight away. C exponential minus 4 t. Okay, so we're just taking the 4 and putting a minus in front of it. The particular solution, because we've got sine t, we need to consider both sine t as a possible solution and its neighbour, its derivative neighbour, cos t as a possible solution. So I'm going to say that that's a possible solution there. I'm going to differentiate it. When I've differentiated it, I then take my differential term, put it into my equation, take my y term, put it into my equation, and then I can compare terms. This time what you want to do is compare your cos terms here. So we've got a plus 4b equals 0, and then you want to compare your sine terms. So minus b plus 4a, and how many sine terms we got on the right hand side? We've got 1. So that's what we're doing here. So that's what we're doing there and there. Okay, some jiggery pokery, a little bit of algebra and stuff. I want to skip over it, but then you can find your constant terms. Okay, so that is the end of the PowerPoint that we did for your first order differential terms, and hopefully this podcast has helped reinforce your knowledge of what we've done in class.